Okay, I think there we go.
Great.
So hopefully
Awesome.
we have it here. And maybe, just kind of continuing here, the technology that we've developed is really directed at the power efficiency. It was developed many years ago. Analog and memory computing, I think, is a very critical technology for power efficiency of AI compute. Um, it was developed in my lab back in 2017. We spent the next period of about 5 years still in the lab, really building full architectures and software, really de-risking the technology. This was all done supported by DARPA and DoD. It was also directly supported by TSMC, who has been following my research for decades, and they gave us access to advanced silicon so that we could build full chips, so on and so forth. They're also investors in the company now and have been very enthusiastic about this technology. But essentially, we spun the company out in 22, and our focus then was on applications that needed extreme power efficiency. And so that led us to markets actually in edge computing, and in particular, what we call client computing. So what Encharge has been developing since basically when it was spun out, I would say since early 23, is chips. We've been working with some of the industry leading OEMs who build laptops. We've been building chips that would be inserted inside laptops to deliver significant compute capability, to be able to increase the kinds of AI that can be done on device. That has led to Encharge's first products, which we call EN100 and EN200, and that's really driven the maturity of our architectures and software. But in the meantime, what's happened more recently is, of course, that power efficiency has become critical in the data center. And so that has pulled us into a number of critical data center programs. And in particular, we're working currently with an industry-leading memory provider that has the dominant market position for HBM to build products that are directed to solve the memory compute bottleneck in data center inference. And so that's really been our focus, I would say, since mid 25. And that's allowed us to accelerate on some opportunities in the data center together with this partner. And that's, of course, also what's driving our focus on planning around capital and so on. With that background, let me share a little bit more about the current opportunity, but I just wanted to give you that little bit of context so that you have a sense of, the maturity of the company and its products and so on and so forth. So with this, if it's okay with everyone, let me go ahead and share some slides so that we can talk a little bit about the current opportunity. Oops, can you see my slides? Not yet. Okay. Can you see my slides now?
Yep, it's coming. Yep.
All right, very good. Okay, so let me share a little bit about the opportunity that we're focused on right now. Now, I have meant to advance my slides. Let me know if you see the second slide. Sometimes it doesn't always advance right away. Okay, very good. So really, the 4 points that I want to connect for you are that first and foremost, we are leveraging a critical technology that we have, and it's an analog and memory computing technology that delivers extremely high levels of energy efficiency. This is on the order of 300 tops per watt for 8-bit compute efficiency. That's really an order of magnitude more efficient than any of the digital technologies that exist today, from both incumbents like Qualcomm, NVIDIA, and so on, and also from any startup that has reported any of their results. I think the second point here is that this is not theoretical. What we've built exists in silicon, and we've built the full architectures around it, hardware and software and so on. And it's on the strength of these two aspects that we now have been able to attract the partnership, very strong partnership of the market leading memory provider, HBM provider, that owns about 70% of the HBM market. And as you'll see, this together with them is allowing us to build what I believe is a very transformative product for solving the critical challenge for data center inference. I won't, dwell on this too much, but I think all of you are well aware that the data center is an enormous market opportunity and something that there's a lot of demand to solve. Okay, moving to the next slide here. Once again, I think everybody understands here that the data center is desperately in need for power efficient solutions. Today, the ability for this industry to move forward is really limited by the power wall that is being hit. And of course, The solutions that we're looking for are quite extreme. There's discussions about attaching nuclear reactors to data centers, putting data centers in space. That gives you a little bit of a sense of how transformative and how critical a fundamental shift is needed to address the power efficiency. And so that's really the opportunity that we have together with this memory partner because of the fundamental technology that we've built and that we've matured. And what I'm showing on this slide is just a first visualization of what this transformation is going to look like. What you see on the left-hand side is what the state-of-the-art architecture looks like today for data center inference. This is an NVIDIA module. And what you see here is basically these solid blocks. That's HBM memory. That's memory. And then in the center, you see these large GPUs. And it's essentially this separation of memory from the compute that is causing all of the bottlenecks that we see for data center inference today. What I'm going to describe for you is the architecture that we are building together with this leading memory partner. And what you see here is only solid blocks. In fact, compute is directly integrated together with this memory, and that's going to be critical for how we overcome the primary bottleneck in data center inference today. Now, if you look at the top line numbers for this system, this is very compelling. This is an order of magnitude lower power. We can run a large model on a single card rather than multiple drawers or trays. But the more important point, as I'll mention, is that this architecture fundamentally aligns with the economics of data center inference. And that's the part that I want to describe for you. If we look at how data center inference is done today, this is really done in two phases for large language models, something called prefill and something called decode. Prefill is this phase where we take essentially an input prompt or all of our input data and process all of those tokens at once. So essentially, you can imagine an input prompt, what is the capital of France? What you can do is, because you have all of these tokens at once, you can bring the data from memory one time and use it to process all of these tokens. That data movement cost gets amortized, and so this can be made very efficient. This is essentially compute bound. You can throw more GPUs at it, and it can be done very fast. The primary bottleneck in the data center today is what we call decode. This is the process where we now generate tokens one at a time. The challenge with this is that you need to bring the data from memory every time. And so this process is entirely memory bottlenecked. Okay? Now, what's important to note here is that this has a two-sided constraint. On the one hand, we need very high memory bandwidth. That's how quickly we can move data from memory, because you need to do this every time for each token. But the second point here is we need very large memory capacity. And the reason is because this data is very large. The model size can be hundreds of billions of parameters, trillions of parameters, and so on. Okay? This memory bottleneck makes decode essentially the 95% cost driver, the big limiter for data center inference. And if we look at the industry today, it's essentially struggling with this two-sided trade-off. Effectively, you can either get high capacity or you can get high bandwidth. You can't get both from the memory architectures we have. Okay, essentially what we have today is the world is divided into two kinds of architectures. Architectures that are based on something called HBM memory and architectures that are based on something called SRAM memory. These HBM architectures, this is essentially what NVIDIA is, these effectively use this high density DRAM memory called HBM. So if you look at an NVIDIA module, you have a good capacity of memory, 288 gigabytes, but because this memory is sitting on the sides, it has very limited bandwidth, only 22 terabytes per second. What that means is we now have this big GPU. This is a big, expensive reticle-sized GPU, but it's memory starved. And so it's underutilized, maybe 10%, maybe 20%. And therefore, this is not an economical way to do data center inference. Okay, the alternative is essentially what Grok does. Here, what they use is a different kind of memory, something called SRAM. That's the kind of memory you can directly put on your chip. Now, because it's directly on your chip, you have very high bandwidth. You have very high density of wires between your memory and your compute. And so this has very high bandwidth, 7x more, 150 terabytes per second. The problem is SRAM is not a high capacity memory. And so here you have about 500x less memory per chip. So now if you want to run a large model, a multi-hundred billion, trillion parameter model, you need thousands of chips, and all of these need to be connected. This is also not an economical way to run inference. Now you have the CapEx cost of all of these chips. You have all of the overheads of running the networking and so on. And this trade-off between capacity and bandwidth is essentially what's causing all of the struggles in the industry, and the entire industry knows this. This is a quote from Jensen Huang after he bought Grok, where essentially what he's saying is that SRAM is great, it gives you this bandwidth, but it doesn't address the models that are dominating the cost in the data center today. It doesn't have enough capacity. Okay, so now what I want you to think about is what would be the ideal architecture for solving data center inference? Okay, and my suggestion is that if you've got a card, let's say you've got a 1,000-watt computing card, you really need all of your resources, all of your 1,000 watts to go towards memory bandwidth, because that's what generates tokens. You want to have as much bandwidth as possible. Compute essentially should be free. Okay, but what's also important is you want to do this using the highest density, highest capacity memory technology. That's DRAM. And so the architecture that we are building, which we call Shale, is essentially this. All you see here is a two-dimensional array of high density, high capacity HBM memory. Okay. You see the compute, what we're going to do is we're going to integrate it directly inside the HBM stack. That lets us create this 2D array, which now means you can scale up the capacity of memory through this 2D array to a very high level, up to 2 terabytes of memory. But in addition, by doing this two-dimensional array of HBM, the cross-sectional bandwidth is also very high. It's at the level of those SRAM architectures. So we want to simultaneously solve for capacity by using high-density HBM, while also achieving bandwidth at the level of SRAM. The key to doing this is creating a 2D array of HBM. In order to do this, we need to put our compute directly inside the HBM stack. Because when you do that, previously, you needed to have one side of your HBM occupied by the GPU. Now, because you don't need to occupy one side by the GPU, you can create this 2D array and scale both capacity and bandwidth as I'm showing here. So what does this look like? An HBM stack is essentially these layers of DRAM, up to 16 layers high, and then you have what we call the base die. That's implemented using a standard CMOS process that you can get from TSMC, you can get from Samsung, and so on. What we are going to do is put our compute accelerator, our NPU, directly inside that base die. That's what allows us to integrate compute and memory to create this 2D array, which lets us simultaneously solve for capacity and bandwidth. Now, if this is the perfect architecture, like I've described it, the big question is, why can nobody else in the industry do this? Why isn't the industry already doing this? And why do we think Encharge can do this? And the answer is thermals. Okay, so it turns out when you put compute inside this HBM stack, that compute consumes power. That power generates heat, and that heat breaks the operation of the memory. Together with this memory partner, this industry-leading memory partner, which has 70%, delivers 70% of the HBM to the market, we have carefully understood exactly how much power budget you have before the HBM stops working. It's about 5 watts. Now, if you think about how much bandwidth this memory gives you, for HBM4E, that's about 4 terabytes per second, that tells you how much compute throughput you need to fully use all of that bandwidth so that you're not wasting it. It turns out you need about 500 TOPS of compute capability. So the question becomes, who can deliver 500 TOPS of compute performance within a 5-watt power limit? That means who can deliver 100 TOPS per watt of power efficiency for NPU? And the answer is only Encharge can. Okay, and the reason is we have this analog in-memory computing technology, which I mentioned to you as this big breakthrough, We've already shown chips running in our lab in 16 nanometer that this can deliver 150 tops per watt at the level of the matrix multiplication. That's the core operation that AI compute does for 8-bit compute. This is much higher than any of the other digital technologies out there. And in fact, it's in 16 nanometer. Okay, these are in much more advanced technology nodes, 4 nanometer and 5 nanometer and so on. Now, what's exciting is Encharge has recently taped out a 3 nanometer chip, and there we see efficiency of our in-memory computing core at 300 tops per watt. So that's further efficiency advantage over an order of magnitude beyond the other technologies. Now, the point I want to make is that this technology is essentially doing the core operation in AI compute. That's matrix multiplications. Okay, but of course, we need to build the full NPU around this so that the architecture can run all of the different kinds of models that we have in the data center. And that's what allows us to get to this 100 tops per watt, okay, with this 300 tops per watt core technology. Now, I won't spend a lot of time on this, but essentially the big breakthrough that enables that efficiency is our form of analog in-memory computing. Analog computing is an approach that we've known for decades can give us much higher efficiency than digital, orders of magnitude higher. The challenge has always been that analog is noisy, and it's hard to integrate into a standard CMOS supply chain and make scalable. What we've designed is an approach that uses the standard metal wires that you have in the CMOS technology to build what's called a capacitor. This has this very high intrinsic precision that gives us this extremely high accuracy for analog compute. This is actual data from our 16 nanometer chips that we have in our lab. What I'm showing here is the transfer function, the compute operation that's being done by this analog technology. In fact, if you look closely here, this is not one transfer function. This is 256 transfer functions on top of each other, all of our circuits working at once. And what you see here is there's no variation. This is perfectly linear. This now solves the problem we've traditionally had with analog, which is noise. Okay, so this is the big breakthrough that gives us the power efficiency that allows us to integrate the compute technology directly inside the memory stack. The point I want to make, though, is that this is not theoretical. We have built many generations of chips that initially focused on this critical breakthrough, the fundamental technology, also built full architectures. And in fact, we built those architectures in a way that now looks exactly like our first product. This is in 16 nanometer technology. This is the full product architecture. As I mentioned, our initial products have been focused on client computing, edge computing, and we're delivering these to partners that will put these inside laptops. But this now is that full architecture with a full software stack, all of the hardware architecture all together. As I mentioned, what's exciting is that we recently scaled this to 3 nanometer. That's the core analog IP. One of the points I want to make, I mentioned that TSMC is an investor in the company. TSMC actually paid for the fabrication of this test chip. That's a very significant validation. Typically for startups, even to get access to the 3 nanometer technology is very hard from TSMC. They have been following our research. They're investors in the company. They've been very supportive to move this technology to their most advanced silicon node so that they can demonstrate that the most advanced architectures run effectively in their advanced technologies. Having scaled this to 3 nanometer will now allow us to accelerate in this joint development that we have with this industry-leading memory partner. Okay, so what is the consequence of doing this? Now, when you have this architecture, once again, the top-level numbers look very good. We have capacity even more than those HBM architectures. The reason is because those only had a few of these HBM stacks. We could now create this 2D array. So we have about an order of magnitude more HBM capacity per card. But what's also important is we've simultaneously delivered bandwidth that's at the level of those SRAM architectures. through this 2D array, you have this very large cross-sectional bandwidth. So now you've simultaneously solved for capacity and bandwidth. Now, what's really interesting is that this architecture fundamentally aligns with the economics of data center decode. When I talk about capacity, because we're using HBM memory, that is a memory technology that's about 20x lower cost compared to SRAM. So in terms of capacity, this is fundamentally a more cost-efficient solution than SRAM architectures. In terms of bandwidth, you remember the previous HBM-based architectures had to have this separate GPU, but the GPU was underutilized because the memory bandwidth was limited. Because we are putting compute directly inside the HBM stack, we now have all of the bandwidth and the compute properly sized to fully utilize the compute. Now, when we scale up the architecture, we scale the bandwidth and the compute in the same way. And so we always operate at the maximum compute and memory performance. So once again, we're not spending, there's no cost inefficiency in either the compute or the memory bandwidth. So this gives us an architecture now that's directly aligned to the economics of data center decode. I just want to talk a little bit about what our development plan looks like and what has already been demonstrated. We already have our core NPU architecture fully developed, hardware and software that's in our labs. You may have also seen data from the testing in our data room. Essentially, we're directly taking those architectures now and migrating them from 16 nanometer to 3 nanometer. That's what the base die is, the base die technology is for the HBM stack. As I mentioned, we've already taken the core analog block and already migrated that to 3 nanometer with the help of TSMC. So all we're doing now is taking the digital architecture in 16 nanometer and migrating that to 3 nanometer. That's going to lead to our first tape out together with this memory partner, which is scheduled for early Q2 2027. So we can have a very aggressive development schedule because we're essentially using the existing architecture, both hardware and software, and just migrating it to 3 nanometer. I won't spend too much time here. I just want to mention that the core product we're building is essentially this. We call this Shale. This is a silicon interposer package that can have up to 36 of these HBM stacks, each of which has the compute accelerator integrated into it. Our first strategic customers, together with this memory partner, are going to be Frontier Labs and hyperscalers. We're in active conversations with them about deploying these in their data centers. These customers build very custom data centers. They use their own ODMs to build racks and to build the full platform. So we will deliver directly this into their designs. We will provide the reference designs, both hardware and software. Now, eventually, we will also scale this to neoclouds and sovereign data centers. They use much more of an OEM model. So there we will build form factor cards and form factor racks to also address those customers. But our first customers, we're going to sell this product into very customized data centers that they build. I've talked a little bit about the efficiency of this module, but I also want to speak a little bit to the implications for the data center. Here, we've done a case study, and we've done different case studies for different kinds of use cases and different kinds of models. This is a 200 trillion token per year facility that's running a very advanced model, something called DeepSeek 3.2. Okay. If we use the current state-of-the-art architectures, those are the NVIDIA architectures, this is a gigawatt facility. If we use the architecture that I described, the Shale architecture from Encharge, this becomes a 160 megawatt facility. That's critical in terms of being able to stand up and start operations for data centers quickly, which today are limited by the power delivery capability. But in addition to that, you can see that the CapEx cost is about 75% less. The reason is because we don't have this big, expensive reticle-sized GPU in the system anymore. which is underutilized because of the limited memory bandwidth. And so that reduces the CapEx cost for all of the compute by 75%. In addition, because we don't have the power of that GPU, this also reduces the operating cost of the data center. And so the cost to generate tokens is reduced by about 80%. So this has very significant data center efficiency implications. And the reason is because we built an architecture that is essentially operating at the limit of the memory bandwidth, which is what generates tokens for data center decode. I just want to talk a little bit now about the market opportunity and the go-to-market pathway. And the first thing I'll say is that we all know that the spend commitment for the data center is very significant, right? $1 trillion spend commitment. I think the critical point I want to make is that we are not building a component that goes into this. It's not a memory. It's not a networking component. This is the critical path, which is the compute accelerator. Okay, so now that we understand, sort of the spend commitment, and in particular the spend commitment around this critical aspect of the data center, the next thing I want to talk about is how big is that TAM and how addressable is that market? And then what is the go-to-market path and scale-up path look like for Encharge? The first thing I want to say is that if we look at the data center, there's many different use cases. And the Encharge architecture, because it simultaneously solves for capacity and bandwidth, has the broadest addressability across those use cases. So some of the use cases involve very large models we want to be able to scale up to. Some of them require very low latency for small models. Some of them require very large context supports. This is essentially to run very advanced agents. If we look at the NVIDIA architecture, it uses HBM, so it can scale to very large models, but it's very limited in terms of its latency for small models. This is the reason NVIDIA bought Grok. Okay, but then if you look at these SRAM-based architectures, including Grok, they give you very good latency for small models, but because they use SRAM, they can't scale to the large models that we need to run in the data center, and they can't scale to the large contexts that you need for advanced agents. Because we simultaneously solve for capacity and bandwidth, we can address all of these use cases most completely without compromise. So there's a large market opportunity and the broadest addressability through the Encharge architecture. The next thing I want to talk about is the synergy and the partnership that we have with this memory provider. As I mentioned, we're working with the industry's leading memory provider, and there's a lot of strong synergies. Of course, from Encharge's perspective, we're essentially taking commodity memory and making it a whole compute architecture. That means we have the NPU architecture, we have the software stack, the reference designs. We're actively working with the data center partners so that we can support the way that they would like to deploy their models on this architecture and so on. Now, in addition to that, though, the memory partner is bringing very strong synergies as well. They're already delivering 70% of the HBM to the industry, so the manufacturing capability is already scaled up. The go-to-market channels, supply chain is already scaled up. The qualification channels are already scaled up. We already have the existing supply agreements with the data center partners, which essentially are going to be converted from commodity memory to this new form of HBM compute. So there's a very strong synergy, and we see here that the go-to-market pathway is significantly accelerated and de-risked with this by the synergy that we have with the memory leader. Here, what I'm sharing is just a revenue model for the products that we're building together with this memory partner. And what you see here are two different product lines: our data center product, that's what I've described, and then the existing client computing products. I want to focus on the data center product for a moment. Okay, we are currently in a very aggressive development schedule with this industry-leading memory partner. This memory partner has been looking for how they can deliver more value to their customers by being more than commodity memory. They approached us in early 2025. They did a worldwide search for a computing partner who could help them move up the value chain. Through that diligence process, they selected Encharge because of the power efficiency of our architecture and because of the maturity of our hardware and software. This unlocks our ability to build an architecture that overcomes the memory bottleneck by integrating compute directly inside the memory. They are investing toward the first tape out. We are doing the first tape out of this product in Q2 2027. They are investing $100 million. That's just engineering in-kind contribution. Okay. In addition to that, they're doing an equity investment. They are co-leading this fundraising round for Encharge. They're also doing a large equity investment. But in addition to that, they're doing $100 million of investment just towards the first tape out. Okay. After that, we will do customer demos and pilots. Those are already active conversations that we're having. That will then lead to the final product that will go into volume production into the data center. And here what I'm showing you is a revenue ramp that's based on servicing through 2033, three strategic customers, Frontier Labs and hyperscalers. I haven't even shown the expansion here to additional hyperscale and Frontier Lab customers or to neoclouds and sovereigns. So this is just showing the customer pipeline through 2033. In addition to that, Encharge has a lot of interest as a critical technology, and we have very significant programs with the government. We have, in the past, over about $30 million of government contracts really focused on advanced development. That's helped us accelerate our 3-nanometer development of our technologies. This is through government grants focused on AI superiority and semiconductor superiority. And we have a very active pipeline of continuing government interest and contributions. I just want to take a moment to mention our team. So you know myself, I want to share that my other co-founder is Achira Iraga. Before Encharge, he was general manager of a business unit and VP of engineering at MACOM. He's delivered some of the most complex and advanced mixed signal chips to the industry for data center in MACOM. My other co-founder is Kailash Gopalakrishnan. Before Encharge, he was an IBM fellow. He led their entire AI hardware software teams and developed the accelerators that are now deployed in the IBM enterprise. And that sort of strength runs all through our leadership team, but it also runs all the way through our engineering team. So we have about 100 engineers, actually over 100 engineers now, and they've come from the top companies, including NVIDIA, including Meta, and including startups like Grok and Cerebras. I'll also point out that we have a very strong advisory board. This includes, for example, the provost of MIT, that's Ananta Chandrakasan, who's also on the board of companies like ADI. It includes the president of Stony Brook. She was previously dean of engineering at Princeton, and she's on the board of Intel and Medtronic and so on. Jim Plummer, Don Rosenberg. So very, very strong advisory board and people around the company as well. We are currently accelerating on this data center opportunity. That involves about a $200 million plan to get us to the point of volume deployment inside the data center. As I mentioned, this is a joint activity and a joint development with the industry's leading HBM provider. We were initially thinking to raise about $200 million. We have currently significant interest in the round, and so we are going to increase that. We're likely going to raise more than $200 million because it's a good opportunity for us to bring valuable partners, investor partners into the company. And primarily, this is going to be used to develop the first product that will tape out in Q2 27. That will be used for various customer demos and pilots. That will also drive the development and tape out of the second product, which will go to volume production and deployment in 28 and 29 timeframe. Okay, with that, let me pause and see if there are any questions, and I would be, of course, happy to answer those.
Yeah, so on the chat, there are 3 questions. So let me go over those. First question was, could you explain why the total power consumption within the HBM stack is limited to 50 watt? Also, why is the energy budget capped at 5 watt? Is there a specific technical reason why the total power cannot be increased to 55 or 60?
Yes, excellent question. So what happens is if the temperature rises too much, what happens is we have these layers of DRAM. We have these layers of memory. That makes it very hard for the heat to escape. But these layers are critical. That's what gives you the high density of memory. But because the heat is trapped, when the heat rises too much, the DRAM stops working. Okay. And so what's critical here is when we consume power, because you're doing compute operations, that power is dissipated as heat, and that heat causes the temperature to rise, which can break the operation of the DRAM. There's very careful thermal and power distribution management that happens in this stack that we use through silicon vias to do thermal conduction and so on. This is the area that the memory partner is experts in. And so based on all of that, that tells us what the power consumption has to be of this base die. And that's what's limited to 5 watts. The total stack, all of the power that's consumed in the memories, all of the power that's consumed in the base die for interfaces is 50 watts, but the power budget for just the compute then is limited to 5 watts. If the temperature goes above that, the heat can't escape because we've got all of these layers of memory, and that can cause the operation of the DRAM to stop. That's the critical limiter for integrating compute inside this DRAM stack.
Next question.
Okay.
Certain pages.
Yeah. Okay. The next question is on page 13. Could you explain why the L2 and L3 caches are treated separately? I thought our core uses SRAM only to select the capacitor corresponding to the weight values.
Very good question. Actually, the way our architecture works, the way any computing architecture works, give me 1 second here. I'm going to go to this non-presenter mode so that I can share additional slides. Can you see my slides still?
Yeah.
Our architecture, let me see if I have a picture of it here. Our architecture looks like this. Here you have this in-memory computing macro, okay? But the in-memory computing hardware is limited. But because we want to run very large models, we need to store those models in level 2 and level 3 memory. Like we have a level 3 global memory here. Okay, so our architectures have already been designed to have the in-memory computing engines, that's what I'm showing here, but also be able to scale the total models, the total workloads we can run by connecting to L2 all the way out to DRAM. So what we've essentially been able to do is in our architecture that we're working on with this memory partner, we can directly take our interfaces from these L2 memories and directly connect them to the high bandwidth that we have for the HBM stack. So we can directly use this architecture for the work that we're now doing to do the integration inside the HBM stack. So the point here is that we have a very general purpose architecture that's allowed us to very rapidly adapt and directly use this for the memory integrated product.
So the next question is that will the on-device or edge physical AI customer product also be based on the ENHVC platform?
Great
It seems
question.
like there might be a overspec for the application. Will the EN100 or EN200 product be used for the segment instead?
No, so very good question. EN100 and EN200 are already developed. EN100 is already in our lab. EN200 is already ready for tape out. And these are specifically for client computing. They don't involve HBM on top of the NPU. Okay. So these are already developed. This is the new architecture, which is really focused for the data center. What I will share is that because the models that are being run on device are also growing rapidly, there's been a lot of interest from our client computing customers and partners to use maybe not 36 HBMs, but maybe use 8 HBMs or 4 HBMs inside a form factor that can actually be used for edge products. And so there is a product concept that we've been developing together with those partners called Quartz, which uses essentially a smaller version of this chip. This is a scalable chip. It has 36 HBMs, but you can also have, so we call that Shale 36, but you can also have Shale 16 and Shale 8. And so you can use smaller versions of these to address essentially edge servers or workstations. And there's been a lot of interest in that as well. But I think what Encharge needs to do is focus on our first strategic customers to move these into the data center deployment where there's very strong demand right now.
Any other questions? All right. So, Naveen, have you finished your presentation, or can you move on to the question list?
Yes, I'd be happy to move on to questions.
Right. So, can I share the screen?
Yes, please do.
Okay, so these are the questions I collected from the potential investors who joined the session today. So there are about 8 questions. Maybe we can go over those. And in addition to the 8 questions, there are a few more questions, but those are mostly confirming the numbers on the data rooms and so on. So you can give us the answer later in the written format.
Sure. Let's start with the first question, should we?
Okay. The first question is about the characterization status of EN100. So can you give us the latest update and the numbers you have tested?
Yeah. So EN100 arrived in our labs on April 30th, 2026, and its bring up has gone extremely well. Within the first 2 weeks, we were able to test all of the functionality of the chip, all of the units, all of the blocks. Remember, EN100 is being used for some very strategic exercises by our client computing customers. They're using it to integrate and test on their client computing platforms for laptops that they're planning to insert this into. So our big focus after we've brought up the chip has been developing all of the tests that are going to be reproduced on the customer side. So I would say since the end of March, we've essentially been working to build all of those tests and to start to integrate them inside the production testing system that we have, the benchtop automatic test equipment that we have, so that these can be run on those client side. So there's some very specific tests that they need to run on their side, and we've been focused on building all of those out. We do plan to run full models and do demos for some of our next customers. So in addition to the client computing customers, we're finding very strong adjacencies to physical AI, drones and robots. And so to be able to do some demonstrations for those customers, we're planning to do some additional model demonstrations, which will likely happen in Q3 of 2026. But in terms of power efficiency and full functionality, we've already verified all of the silicon is running at target. And so that's essentially what we have in our lab. And I can pause here to see if there's any other questions about that.
So the characterization data in the data room is not up to date. I think it was dated like May 31st or so. So is there any update since then? Is there any updated document?
What I would say is most of the focus since the initial bring up of the chip has been in developing the specific tests that our client computing customers are planning to run. So a lot of the update has been focused on doing those tests and building out those tests so that we can deliver them to those customers. The additional demonstrations, general purpose demonstrations, we will primarily do in Q3 2026. But essentially what I can confirm is that, sort of in that time, in the time so far, we fully validated all of the functionality of all of the blocks. The power and performance are all at the targets that I've reported in our product specs.
Any additional question regarding the number one? Okay, then let's move on to the number two. So yeah, so it's about the competition, like a Samsung has like a PIM computing memory, or other vendors have the similar technology. So what's your view on the competition with the similar
Yeah, great
technologies?
question. So, processing in memory was a concept that Samsung and SK Hynix and many other were working on, where they essentially put compute on the DRAM chip, on the DRAM die directly. And this was for both LPDDR memory and other forms of DRAM as well. The problem is that what they put was some very simple compute, essentially things that would do matrix multiplication. The challenge with PIM architecture is that in order to run full workloads, there's many other operators we need to do, and all of this needs to be compatible with the software stack. When you just do a single operator inside the memory, your software is not designed to basically make sure the data that you need next to that compute is properly positioned. The software is designed to treat the memory as one unified memory. So part of the innovation here is, of course, that we're putting the full compute accelerator that has all of the architecture support that we need to run full software, full models directly inside. Now, not the memory die, but inside a logic die that is directly below the memory. That's important because logic die is typically a lower performance process. It's designed to be very cost effective for memory. But logic has higher performance transistors. You need this to build the full architectural infrastructure. We need floating point units. We need all of the programmability supports. So by having the logic die have the full NPU, now we have the full architecture that lets us run the entire model. This enables compatibility between the hardware and the software so you can run full models. So the big challenge with PIM in the past was that you didn't really have an architecture that was compatible with the full software that's needed to run models. And so this architecture, because we can put the full NPU, it's so power efficient, we can put the full NPU inside the base die of the memory. And because the base die is a high performance technology, not a low performance memory technology, now you can run that full architecture at high performance, high efficiency, and with all the software compatibility that's needed to run the model. That's the big breakthrough. And it comes because we have very high power efficiency for the full NPU and the software stack, of course, that's compatible with that.
So there's an additional question regarding this number two. So
Yes.
can you clarify the risk that SK Hynix could internalize similar technologies or
Yeah.
collaborate with other companies other than
Great question. So the
Encharge?
first thing I would say is that our technology is very differentiated, and we're working closely with SK Hynix now. This technology is not easy to replicate, of course, because the core analog technology has a lot of know-how and a lot of IP patents, but also the architecture and the software has a lot of IP and a lot of patents. Okay? So it's very hard technology to replicate, and this is the critical technology for unlocking this architecture where we need to meet the thermal constraints of putting compute directly inside HBM. Now, we have a very strong relationship with our memory partner here, but we also want to make sure that Encharge has full optionality to work with other memory providers, both because of business reasons, but also because of need to secure supply chain. So we have very deliberately not had any exclusivity terms inside the JDA, because if we have exclusivity terms, we'll have reciprocal exclusivity terms. We have also very deliberately not have any NRE terms. So we don't get NRE payment from the memory partner. The memory partner is already putting in over $100 million of engineering contribution of their own towards the joint tape out. But with NRE, you will often have IP encumbrances. And because we want to be able to maintain full control of our IP and full optionality, we don't have those terms together with the memory partner. Now, the question though is, what about the risk that SK Hynix could work with somebody else? SK Hynix is only working with Encharge. Our memory partner is only working with Encharge on this technology. And as I mentioned, it's a significant investment. They're putting in $100 million of engineering investment just for the first tape out. Okay. Beyond that, there's the whole 3D integration, the development of the package, and so on that they're also contributing towards. So a very significant investment. I also mentioned that this is strategically important to them. They're co-leading the round and doing a very large investment in Encharge, equity investment in the round. The other thing I'll say is the joint work we're doing together is really driving a lot of stickiness of Encharge's architecture inside this HBM computing concept. Today, for example, the base die architecture is driven entirely to be compatible with Encharge's architecture. The firmware from the memory partner is getting integrated inside our firmware. So there's a lot of ways in which we're creating a tight stickiness that's required, sort of and that requires the Encharge partnership towards this product.
All right. So
I see
any
the
additional
question. The
question?
next question is about Qualcomm's HBC
Yeah.
project.
Mhm.
And I want to share a little bit about this. So HBC is a similar technology, but it's different. It doesn't use HBM. It uses what's called custom memory, a 3D stacked memory that's hybrid bonded on top of the base die. We have a very active roadmap around hybrid bonding as well. I want to point out today, hybrid bonded memory is not a standard supply chain technology. Okay. The reason that we focused on HBM first is HBM and the ability to integrate IP inside the base die is an industry standard supply chain. And it has a very fixed timeline and a near-term timeline. This technology, hybrid bonded memory, like the one that you've heard about from Qualcomm, is not a near-term technology. There will be initial product demos that will happen in 2028, and we are working with the memory leader that's going to essentially be able to scale that up to the data center level. But together with them, we are actively planning and helping them plan what should be the DRAM design for those. But the first step, the first product, is really based on the existing supply chain, HBM. So it's a very active roadmap. Once again, Encharge's architecture is going to be critical for unlocking this. Also, hybrid bonded DRAM is limited by thermals, just like integration of HBM, integration inside HBM is. So we will always have this advantage as you go to any kind of 3D integrated memory technology, but our focus is to work first on the one that is standard supply chain that can be delivered at scale, and then to migrate and move over. And we're actively doing that together with our memory partner towards these other new forms of memory as well, which can deliver more bandwidth and scalable number of layers and things like that.
Right. The next question is about the JDA with SK Hynix. Have you, fully executed it, or if so, can you share some key terms?
Yeah, the JDA is fully executed. We actually have a summary of it, and I can share that with you, June, and you can we can provide that actually through a secure link. But the JDA is fully executed, and we are actively delivering on all of the project milestones and on track for that Q2 2027 tape out.
Okay, the next one is about the HP and Dell partnership. So
Yes.
seems like it's like a evaluation agreement and so on, and especially the Dell partnership was signed in 2023, but it was an 18 months term. So is there any extension or something?
Yeah. So because we now have EN100 in the lab, actually we are working to define exactly what the process is going to be and what the evaluation steps are for EN100 and EN200. So all of these partnerships are still very active. In fact, they're still current. But because we now have the silicon in-house, we're working to define all of the next steps towards the integration inside their architectures. So we're actively working that with them now to define the next phases towards their integration inside the laptop platforms. And so
So
those
you're
will be
preparing
updated
the
as we, yeah, those will be updated with all of those new data as we start to deliver the silicon to them and align on the next collaboration plans.
so you are working on the agreements with them.
Yes, right.
Okay.
And these are really now being redefined because we have all of the silicon in-house and because they have new models and workloads that they want to be able to evaluate and demo. And so that's really what we're working with them to align on.
Next question is regarding the license from Princeton. Can you explain the nature of it?
Yeah, so we have a exclusive license with Princeton for the perpetuity for the full lifetime of the patent. All of that is active and continues to be very well supported by Princeton. It's 5 foundational patents that cover the core analog and memory computing technology, also some of the core architectural design aspects of the technology. Of course, in
Is
addition to the Princeton IP, which we licensed into the company now has a very broad portfolio of its own IP that's been developed within the company.
and all the first bona fide sale milestone is satisfied, or is
All
there
of it
any?
is, we are in compliance with all of the aspects of the Princeton license agreement.
Next question is regarding the projection, revenue projection of 226 million in 2030.
Yes.
And
Yeah. So I think the question here is how are we going to meet those revenue projections given capacity constraints in the supply chain, right? Both for the CMOS base die and for the HBM. One of the very important aspects of our partnership with SK Hynix is what we've modeled this as is a sell-through model. So essentially, for all of the HBM that SK Hynix has planned to develop, we are assuming some percentage of that will be converted to this higher value NHBC and shale product. Currently, we've modeled that as a 15% a replacement rate. But what's important is because that's already capacity that's been allocated, it's really not additional capacity that's needed, either on the CMOS base die, the 3 nanometer base die, or on the HBM. So we don't need additional capacity beyond what SK Hynix already will have committed for its HBM to the industry. Now, of course, in order to allocate that capacity, SK Hynix, this needs to make economic sense for. So what's very important is that the unit economics of our joint partnership involves a revenue sharing agreement. And based on that revenue sharing agreement, is what's led to this revenue model. This is the revenue just for Encharge, but actually the revenue sharing model for SK Hynix is very profitable. It allows for about a 3x higher ASP because they're not selling commodity memory anymore. It's the full compute product. So that creates a much higher value for that product. And it's about 11% higher margin So for them, allocating capacity to this joint product is more profitable, and that's what's critical. And we don't seek additional capacity for either the CMOS or the HBM.
Okay. So we talked about the JDA already, so we can skip this part. And number seven, so I think you already explained the background, but Samsung Ventures is in the cap table, but you signed the JDA with SK Hynix, so and the background of it, and yeah, so can you explain this again?
Yeah, so I think the very important dynamics here is Samsung Venture has been a very supportive investor for Encharge. And actually, we've had a lot of conversations with them about compute and memory integrated architectures. But the industry leader today is SK Hynix. And if you're the industry leader, your biggest focus is on building the next generation product that continues to drive differentiation. If you're an industry follower, like Samsung is, your biggest focus is on catching up to the industry leader. So what we found as we started to engage with SK Hynix is a very strong alignment towards building this next generation product. And they have a very strong conviction around that. That's why they're co-leading the round. That's why they've invested heavily inside this joint development program and so on. But of course, as I mentioned, from Encharge's perspective, it's very important for us, even though we have a lot of strong synergy with SK Hynix, to maintain optionality to be able to use Samsung, but also Micron in the future. So I think it's very valuable that they exist on our cap table. And it's also very important that we structure the partnership with SK Hynix that allows us to use other partners for this. But currently, SK Hynix has a very strong conviction around this joint product. And it's also beneficial to Encharge that we have Samsung on the cap table.
Okay, the last question. So the current collaboration with SK Hynix just for the base die, but if is there any possibility that there will be like a deeper integration inside like a DRAM stack, I mean DRAM chip itself? I know it's technically not viable, but
No, actually,
any
June, it is technically viable. The most important thing is it's not industry standard supply chain. So today, SK Hynix doesn't let you customize the DRAM, right? We don't have a foundry model for DRAM like we do for the logic die. But of course, because we have a very close partnership with SK Hynix, many opportunities are opening up. I talked about the custom 3D hybrid bonded DRAM and the ways in which we're partnering towards the next generation DRAM planning for hybrid bonded DRAM. Actually, one of the reasons that I'm here in Santa Clara today is we had a big meeting with our SK Hynix partners to talk about many future directions. And it turns out that there are interesting ways that we could think about incorporating our computing technology directly inside the DRAM as well. I would say those are not near term. Our biggest focus is on using industry standard supply chain and scaled manufacturing capability to deliver products to the data center quickly. And so that's what an HBC is, this HBM integrated compute. But there's many other opportunities in the roadmap that we are actively discussing with our memory partner as well.
so that's all from the question list I have. So
I
is
think
there
there's
any
also some
additional?
Yeah, there is
questions.
a couple of questions in the chat room.
Oh,
Yeah, I think
okay.
there's some questions on the chat. Could you help me? I think some of them I might need a translation.
Yeah. Where is it? I cannot open it.
No, just saying, as you're here, just wanting to ask a couple of more questions, and the questions are all in English, so I think you can easily answer them.
Oh, the English question. I see there's some questions in English. So the first question is, if we segment the decode accelerator market with large and long context workloads, leaning towards Encharge and small, low latency workloads leaning towards SRAM-based players, do you see players coexisting in their own segments or ultimately consolidating? If it consolidates, Is the deciding factor raw hardware efficiency, or which platform and distributed channel you're attached to? And conversely, what's the scenario in which Encharge loses this segment? This is a great question. So I think you do see that there's all of these different use cases: big models, small models, big contexts, small contexts. I would say that the dominant, sort of economic pain point in the data center today is big models, 5 trillion parameter, 10 trillion parameter models. And those require high capacity, but also high bandwidth. And that is something that Encharge uniquely delivers. If you start to see, sort of the small models also emerge, those will not be the big economic drivers of the data center. And so I believe the buy decisions, the spend decisions from data center customers will be driven by their most economically critical models. And so that's why we think that an architecture that can provide both capacity and bandwidth simultaneously is most important. But there is one important direction that I should mention. When I describe HBM, the picture I showed had up to 12 layers of DRAM in the stack. Sorry, up to 16 layers of DRAM in the stack. Okay. Actually, the truth is you can have fewer layers. You can have 4 layers or 8 layers, and that impacts the economics as well. So one of the things that we are actually working closely with our memory provider is to figure out if we should have lower capacity SKUs that give you even more economical solution for small models, or if we should only have the large capacity SKUs, which are, I think, what is really driving the infrastructure decisions for data center players today. So I guess the point I'll make is our architecture, by simultaneously solving capacity and bandwidth, can fundamentally be more cost effective than SRAM-based architectures. And so I think we have a distinct advantage here that we see the data center operators are very well aligned to.
Second question.
Yeah, and there's a second question
The
related
second
to the
question is, could you
financing.
walk us through why the Maverick investment is structured in 3 tranches, and are later tranches tied to any technical or business milestones, or are they purely time-based? Great question. So of course we have a lead, very, very strong lead. Maverick Silicon is one of the most well-recognized investors in advanced computing and semiconductors. Maverick is currently in between funds. So they have a very high conviction about this investment as well. And they did not want to wait to be able to close the deal. They wanted to do the investment. And so basically they're prioritizing their first capital call on their new fund towards the Encharge investment. And that's why their first investment of 60 million has, sort of 2 closings associated with it, because they wanted to, close and commit and not hold up the round. But the first capital call that they will make for the new fund will directly go into the Encharge investment. In fact, they want to do an additional investment beyond that of $60 million further investment from their new fund. And so they will do that investment, and it's only determined by the closing schedule for that new fund. There is no milestones, technical milestones tied. It's really just based on the closing schedule for their new fund. So I think Maverick has a very strong conviction around this. In fact, they wanted to invest not just the initial 60 million, they wanted to have further investment from their new fund. And they are prioritizing the capital call before the fund closes, even towards the Encharge investment, and then trying to do an additional capital call for the additional investment.
Naveen, last question from the line.
I think there was
So
one additional question.
Yeah, you're muted.
You're muted.
Yeah,
Minshik, you're muted.
Yeah, I think there was some echo on Minshik's side, and that's why he muted himself. Minshik, if you like, you can type the question into the chat.
Excuse me. Oh, one more. I will try. Okay. Just,
Yes,
Very, very brief.
I can hear you. Yep.
Would there be any possibility for JEDC, for example, to raise the total thermal budget itself in the next generation standard? For example, if the cooling methods that bring coolant directly beneath or alongside the stack, such as two-phase cooling, for example. So if that situation comes, could this also be a good opportunity for Encharge AI?
That's a great question. So actually, because of the DRAM stack all having to be very close here, up to 16 layers, unfortunately, bringing the cooling inside is very challenging. And so that will kind of keep a very tight thermal budget. Now, actually, that tight thermal budget is what makes Encharge such a critical technology for this data center product. And that's why I think that we will remain such a critical technology. But what is very interesting is if you used fewer than 16 layers, I mentioned that there could be 4 layers or 8 layers, and these might be interesting as you maybe want to address smaller sized models. Today, the data center economics is dominated by the large models, 5 trillion, 8 trillion parameter models, and that's primarily what's driving the decisions for the data center infrastructure. But if you had fewer layers, this could now, coupled with new computing technologies, help increase the thermal budget, and so on. But I think one of the strong advantages Encharge has is that we can deliver adequate compute performance under that thermal budget. And so that's a big advantage, right? And if we want to deliver more compute, we can actually scale out by having more of those die as well. Now, of course, there will be some cost associated with that rather than putting just more compute within one die. But that's where we can build different economics for the SKUs by having fewer layers, right? If you have more die, you now don't need to have 16 layers. Maybe you can have just 8 layers. And now you've distributed the compute. And so that automatically addresses some of the thermal concerns. You couple cooling on top of that, right? And now you can start to address more use cases. But I think the critical unlock is because Encharge has such a thermally efficient technology, we can push the boundaries of the compute capability integrated inside the memory more than anybody else can by an order of magnitude. But you're right, we have all sorts of different design options between cooling and also the number of memory layers. And this is one of the strong advantages of working so closely with such a big memory partner.
Thank you, Naveen.
Naveen, I have a question regarding the term sheet. So I understand that Maverick has in between two, funds, but the window will be open for more than like 8 months, right, from the initial closing, right? And
Yeah.
it's giving too much, benefit to Maverick.
It is a big benefit to Maverick, but I will say, they're a very strong partner, right? They want to lean in heavily into the round, and they're a very strong partner. They bring a lot of credibility and so on. So I think they're a strong partner and a sort of good player to have here. The other thing that I will say is that they believe that they will be able to do that investment much sooner than 180 days. So they did give a sort of outside date, a longer timeline than what they expect. But I think the big focus here is, we want our strongest partners to lean in heavily into Encharge. That benefits the company. And so, I think that they wanted to set the price now. They will set it in a way that there is no conditions or milestones required, right? That will all be expressed in the documents that we have together with them. So we do want them to, sort of lean in and be committed now. And I think that that's beneficial for the company. And this is mainly a timing issue with their next fund. They are in between the two funds. But, we do want to see our strongest partners lean in heavily into the company.
And Hynix is coming in for the initial closing. Is that correct?
Hynix is coming in for the initial closing, and Hynix is investing at a very significant level. They have about a $40 million request, and they've asked for more.
And the timeline for the initial closing would be still like mid-August or late August.
Exactly. It'll be about late August. I'm working now to get all of the allocations sorted out. As you know, June and Ho-chan, we have very significant demand for the round right now. And so I'm working to try to manage all of the allocations between our internals and pro ratas and also all of the new investor interest that we have. And, all of the significant investment ways that the lead and co-lead want to lean in.
Right. If there's no additional questions, maybe we can just wrap it up. Time's almost up, so. Any other questions? Okay, then. So thank you so much for everybody joining us today. And especially Naveen, thank you for your time today. It's very late. You are in Santa Clara, right? So okay.
I'm in Santa Clara. Yes, it's a little bit earlier.
Not too bad.
Not too bad. Very good. Well, thank you, June and Ho-chan, and thank you to everyone for joining. And I'll be available if there's any other questions and so on.
Great. Awesome. Thank you so much.
Right, thank you.
Thank you.
감사합니다.
Bye-bye.
Bye-bye.
Bye-bye.